Okay, good morning, guys. We're at 6.2a in indefinite integrals. And before we get going, I just want to make some definitions here. And some of the definitions I'm talking about is, what is this guy right here? Well, that guy right there is the antiderivative command, and what it's called is the integral symbol. But remember, it's the antiderivative command, okay? And also, if I look inside my integral right here, my f of x, what that little guy is called in there, that's called the integrand. Just like what's underneath a square root symbol is called the radicand. This is the integrand. Well, what does this dx business here mean then? What's about this dx? Well, that dx is actually the variable of integration. Okay, it's the independent variable of y, or of our antiderivative. It's the independent variable. Okay. So what we have done before is we've been working with definite integrals, where we have the integral from a to b of f of x dx. And notice it's a definite integral, and I know it's a definite integral because notice the limits of integration. It has an a and it has a b. There's actually numbers on the integral, and when I take the antiderivative command, what I am supposed to be doing is evaluating big F at B minus big F at A, and that equals some number, right? And that number actually comes from a Riemann sum. It comes from a Riemann sum, which is a whole bunch of rectangles added up together. And we know that number may be positive, it may be negative, it also could be zero, and it may or may not represent the total area between the curve and the x-axis, right? Okay, so we're beating that one down a little bit further again. So this is an indefinite integral. Well, what do you notice about What do you notice about an indefinite integral? They're very distinct. Different is there are no limits of integration. Okay, so when I find an indefinite integral, there are no limits to evaluate. So what comes out of an indefinite integral is big F of x plus some constant c. And that constant c, remember, that little bugger is really important because this big F of x plus my constant is a whole family of functions. And it's an entire family of functions because of that c value. We saw that yesterday or the day before in the slope fields, okay, where that c value just vertically shifts our f function up or down. In all of these functions within this family, they all have the exact same derivative, and their derivative is little f of x right there. It's that little guy in there, and they don't differ by a constant in their derivative, but their antiderivative does. Okay, so that's the difference between a definite integral and an indefinite integral. A definite integral equals a number when we are done. Okay, and we will evaluate definite integrals. Indefinite integrals, they are going to be the antiderivative of little f with a c tagged along at the end. Okay? Now, what are you talking about here? Examples. Well, I got a couple examples here. The first one, remember, there's no limits, but remember, this is a command that says, please find big F of x plus my constant c. That's what it says. It says, find all the functions whose derivative is x squared minus sine x. So we can do that, and it's really not any different than we did before. Okay, what we were doing the day before is we were saying, oh, dy dx actually equals x squared minus sine x, and it said solve for y. Okay, solve for y. That's what we were running into before, a differential equation written out that way. Well, these two mean the same thing. It's just like we did before in 6.18. Find the antiderivative, except now it's not getting all fancy saying, oh, here's here's my derivative, solve for y. It's saying, hey, use the antiderivative command, and that's telling you to find the antiderivative, where the antiderivative of x squared is going to be some x cubed. And to get my 1 here, I know I need to multiply by a third there. And I also need to know that this is minus sine x. Well, the antiderivative of sine is a negative cosine. So that's going to be a plus cosine x plus a c. And remember, as you are going along, you're always taking the derivative of that to make sure it spins back to the x squared. Plus the derivative of cosine is negative sine, so that's where that guy comes out. And don't forget your plus c. So this is what my antiderivative is, or that is the indefinite integral. And remember, this guy here is saying find all my functions, c. So that plus c, if you're missing it, you're going to be missing a lot of points on a test as well. Okay, so why don't you just hit pause for a second here, please, and why don't you go do number 2 and number 3. And what I'm going to do is, I'm going to do them and we'll come back and see if you're right. So I'm going to hit pause. Okay, see, now when you're back here, what I always like to do, and yes, I typically always do that, I'm going to rewrite any exponent that I know can be negative so I can find its antiderivative easier. Okay, and this little guy right here, that's in a template on the green sheet I gave you if you were in class this week, and if you weren't, hopefully you printed it off. But the antiderivative of 1 over x squared, hey, that equals negative 1x to the negative 1 minus the antiderivative of 1 over x squared plus 1. Well, it doesn't matter if it's x squared plus 1 or 1 plus x squared. That denominator is still the same. That's an inverse tangent x plus c. Know your derivatives so you can move on. And then I'm going to rewrite this with my negative exponent. I'm just going to call it negative 1 over x minus inverse tangent x plus c. That is what this is a definite integral because there's no limits of integration. Number 3, when I look at my 1 over x, okay, I'm still going to come over here and I'm picturing it like this, but when I anti-differentiate that, I'm like, oh, that's x to the power of 0. Whoa, something's going weird. Whenever I get that exponent of 0, hey, that's going to be a natural log minus 2e to the x plus 3x plus c. And if that's what you have written there, okay, you're right to this point, but now we're going to learn this isn't the antiderivative of 1 over ln x, or 1 over x. It's not ln x, okay? It's actually the ln, the absolute value of x. So anytime I anti-differentiate these, I need an absolute value in here. Sometimes it may come and go, and you're going to ask me why, and I'm going to tell you why it is. Well, let's come through. Let's investigate this for a second. Why is the integral of 1 over x dx equal to the ln of the absolute value of x plus c? Well, if I have that little note down there, recall the ln of x has a domain of x's that are greater than 0. Remember, we can't plug negative values into logs, okay? But if we're looking at, when we did an area sketch, when we're thinking of it the other way, if we're looking at that derivative of 1 over x, well, the domain of 1 over x is all real numbers except 0, right? So we can kind of look at this a little bit. We're going to think of our graph here. My 1 over x is going to go kind of like that. And we know we also had another one over here. And that's not symmetrical enough for me, because there is a lot of symmetry on this guy, and it's going to kind of come across here. And what this integral, so what we're going to do, sorry, I'm kind of scrambling here, but we're going to consider the integral from negative 3 to negative 1 of 1 over x dx. We're going to investigate, we're going to show you why we have to have an absolute value here in the antiderivative. Well, if I look at this graphically, we're looking from negative 1 to negative 3. So we're looking at this area, okay? Looks pretty harmless. I think we can probably understand that. Like, oh yeah, we know even more than that. We know that that area is even going to be a negative value because it's below the x-axis. Well, that's all fine and dandy. But if I didn't know that that the antiderivative of 1 over x is the ln of the absolute value of x, well, I'm going to run into a hitch because I'm going to come through here and I'm going to try to anti-differentiate this. I'm going to say, oh, easy stuff here. This is the ln of x, and we're going to evaluate from -1 to -3, and we're going to run along, and we're going to say, oh, that's not too bad. That's the ln of -1 minus the ln of -3, and then you're going to try to type this into your calculator because you don't know what the natural log of -1 and -3 are. You're going to be like, whoa, whoa, my calculator can't even do it. Well, why can't it do it? Because I can't have negative values inside my natural log. So what we're going to do here is we're going to kind of look at a symmetrical area of this, okay? And I hope you agree with me that if I look at this area from 1 to 3, this area over here, because of our parent functions, we know that is a very symmetrical area. So we know, if I look at the symmetry, that the integral that we're considering should definitely equal the integral from 1 to 3 of 1 over x dx, okay? Which is going to give me the ln of x evaluated from 1 to 3, which is going to give me the ln of 3 minus the ln of 1. And we can type that into our calculator and we can get it just fine. And if we forget the ln of 1 is 0, remember your properties of logs. Oh, I'm subtracting 2 logs. That's the ln of the first one divided by the second one. So this is actually going to equal the ln of 3, the red area on the positive side, okay? And what we're going to find out here, this pink area, that pink area is actually negative ln of 3 is actually what that area is, okay? And if I wanted it as a decimal, I could. But if I come back and I reconsider things, I'm like, okay, my absolute value is there, and I throw my absolute values here and here. Well, what does that absolute value do to negative values? Well, it turns them positive to it, doesn't it? So this is really, in the end, this is going to actually give me, oh, it's the ln of 1 minus the ln of 3. And again, if I forget all this stuff, I can really see this. Well, I can say, oh, I know the ln of 1 is 0, so this is going to equal negative ln 3. Okay, so I can see that. But if you're like, oh, I didn't remember the ln of 1 is 0, how am I going to get there? Well, same old, same old. This is going to equal the ln of the first one divided by the second one, which is actually going to equal the ln of 3. Ooh, I can raise that to the -1 power and turn it out of a fraction. And then I can use my property of a log, and I can pull that exponent out and say, oh, it's the opposite of the, ooh, that's crappy. I can use my properties of logs, and I can, oh, this is negative ln 3, woohoo, and I'm happy as a clam, and I get it. Okay, but a proof cannot be used with numbers. Why? That thing needs to be the absolute value of x. So I'm going to take you one more page deeper, and we're going to try to look at a formal proof that the integral from 1 over u du equals the ln absolute value of u plus c. So basically, we are proving that the derivative of u of the ln absolute value of u plus c actually equals 1 over u, okay? And you're like, well, how come that's just 1 over u when it comes out of there in that absolute value? Well, we're going to come through here. What does the absolute value actually do? Let's just make sure whatever comes out of it is positive. So there's technically 2 cases that we're going to be looking at, okay? And we're thinking, does little f here really equal big F prime? Okay, so is big F prime, if I take the derivative of this, does that really equal back is what I'm kind of looking at. And so this is what, like I said, this is what we are proving, okay? So there's 2 cases to look at. First case is if u is greater than 0. Well, if u is greater than 0, this is some positive quantity, right? And if it's a positive quantity, well then the derivative with respect to u of ln absolute value of u plus c, well, that really equals, well, if I take the absolute value of a positive number here, or a positive thing, what does the absolute value do to something that's positive? It does absolutely nothing. So this is the same as the derivative equaling, not equaling. It's actually the derivative because it does nothing if that's a positive quantity. If u is greater than 0, then I'm really taking the derivative of the ln of u plus c, which is going to give me, well, the derivative of the ln u, well, what is that? It's the derivative of the business over the business, which is 1 over u, okay? And really, it didn't do anything because it was negative. That is not the case we're worried about. The case we're worried about is down here, if u is less than 0. Well, if u is less than 0, okay, that means u is a negative quantity, right? That's what it is. So, as I'm thinking, if u is a negative quantity, well, then the derivative d du of the ln of the absolute value of u plus c, okay, if u is a negative quantity, and I take the absolute value of it, then what comes out of it? Okay? If u is a negative quantity and I take an absolute value, then what comes out? A positive value, right? Well, a positive value does come out. It's the opposite of what I started with. So I can think of this as the derivative of the ln of the opposite of u, because the opposite of a negative is a positive, right? So if I think of what's coming out of that absolute value here, well, it's the opposite of u. And if it's the opposite of u, when I plug a negative quantity in here, it's going to turn it positive, right? That's going to make it positive. The opposite of a negative is a positive. And then if I take the derivative of this, okay, well, what is the derivative of the opposite of u? And the derivative of the business is negative 1 over what? Negative u, which what does that equal? 1 over u. Derivative of my c is still gone because that's a constant. So we find out that that's why it's the absolute value of u, because if I put the negatives in there, I'm actually going to get a positive coming out, and this is kind of the formal proof, knowing that if u is a negative quantity, what does the absolute value do? Well, it's going to take the opposite of what it was when it comes out, so that's my opposite, and then if I take the derivative of the opposite, I get the derivative of my negative u, that's negative 1, over my negative u, that's going to give me 1 over u, so that's why this proof works. That's why the ln, the derivative of the absolute value of u equals 1 over u. So, what are you preaching and praising for now? Well, I'm pretty much done, but what I'm saying is any time, and you're going to get a little confused on here, but if you're taking the integral of 1 over x dx, you can no longer call that the ln of x plus c. That's no good. It's not going to work anymore. You're going to have to now begin to call this is going to be the ln of the absolute value of x plus c, because I cannot evaluate negatives in my log, okay? And then you're gonna end up running through some of them, and you're gonna look at the back of the book, and you say, "Oh, Mr. Kruger, how come this one doesn't have an absolute value on it?" Well, when you do your antidifferentiation, and I'm just going to throw one out, I'm going to say the antiderivative comes out to be something like x squared plus 1 plus c. Do I need an absolute value on that? I don't, because if I'm putting a negative value for x in here, I'm squaring it anyways, hence it's going to make this a positive value, so the function is going to take care of any negative values for me, okay? And what are you talking about? Well, let's say I was after the integral of an x squared plus 1 with a 2x on top, and that's a dx. Well, I'm kind of looking at a chain rule right here, okay? yeah, I really kind of am, and yeah, I really, no, that's a bad example. But I'll have some coming out yet. But just know that that's why sometimes the absolute value bars are missing. And if you want to put them on them, you can. You want to always default and put absolute values, as you probably should when you're anti-differentiating and you get a natural log. Put them on there, just that when you go to the back of the book and you see some of them do not have that absolute value and they're just kind of giving them a hug with parentheses, that's because whatever value for x that gets put into that function, the function's going to take care of any negatives, and it's going to be an ln of some positive value anyways when you evaluate it. And that's the only time they're going to drop off. Okay? So you do have a few problems to do for homework. I'm shutting this one down. It's a world land speed record at 21 minutes. Hope you guys have a great weekend. I'm really looking forward to seeing everybody on Monday, and we can get hopefully a little interaction going in class. Have a great weekend. See you on Monday. Bye-bye.